Hello everyone and welcome to Control Engineering Tutorials. In this tutorial we will solve this very important problem that every control engineer needs to know how to solve. Namely, the problem is to test the stability of this third order transfer function. Well, before I start I need to mention the following. This problem might appear in control engineering interviews, since everyone knows how to compute zeros of a second order transfer functions or poles of a second order transfer function. However, over here, an interviewer might give you a third order transfer function, and he or she might ask you the question, how are you going to test the stability of this dynamical system? Let's learn how to solve this important problem. The stability of this transfer function is determined by zeros of the polynomial in the denominator. That is, one approach would be to compute the zeros of this polynomial. Now, this is a third order polynomial, and although there exists a formula for computing the zeros of a third order polynomial, the formula is quite complex and maybe 99.999 people do not remember the formula. Here you're left with several options. Either you can guess zeros and then try to divide this polynomial by one of the zeros in order to get the second order polynomial, and then you can further find zeros of the resulting second order polynomial. However, this might be a time-consuming task, and in the case you have complex conjugate zeros, this might become quite complex and computationally intensive. So what is an alternative approach? Well, the alternative approach is to use the Routh-Hurwitz test. That is, without explicitly computing the zeros of this polynomial, we can actually determine the stability properties. And this is very important. Every control engineer needs to know the Routh-Hurwitz stability test. Let's learn how to apply this test on this example. The first necessary condition for the stability of this transfer function is that the coefficients of the polynomial in the denominator have to be positive. That is, over here we have 1 multiplying s to the power 3 and 1 is obviously positive. Then 6 is positive number, 11 is positive number, and 6 is a positive number. Consequently, the first condition for testing the stability is satisfied. However, this is only a necessary condition. We need the necessary and sufficient condition. The necessary and sufficient condition follows from the Routh-Hurwitz test. I will write down the name. The name of the test is Routh-Hurwitz test. The first step of this test is to construct the so-called Routh-Hurwitz table. The rows are associated with the coefficients of the corresponding terms over here. The first row will group the coefficients associated with s to the power 3. The second row will group the coefficients associated with s to the power 2. The third row with s to the power 1, and the fourth row with s to the power 0. So how do we construct this table? The first row of this table consists of this coefficient, then we skip this coefficient, and then we add this coefficient. So it's 1, 11, and over here we have 0 over here. Consequently, we will add a 0 over here. The second row associated with s2, s to the power 2, is constructed by taking this coefficient and taking this coefficient. Consequently, we write 6, 6, and 0. The remaining rows are constructed recursively by using these two rows. And let's construct the third and the fourth row. The first entry in the third row of the Routh-Hurwitz table is constructed like this. It is equal to ratio of, in the denominator we have this entry over here, that is we have 6, and in the numerator we have a determinant of a matrix whose first column is this column and the second column is this column. So let's write this. We have 1, 6, 11, 6 with a minus sign. These vertical bar denote the determinant. Similarly, the next entry is again the ratio of this entry over here, and again we have a determinant of a matrix formed by using this column and this column. Consequently, we write 1, 6, 0, 0, and we need the minus sign. Obviously, this entry is equal to 0. However, how about this entry? Well, let's compute this entry over here. We need to compute the entry, and let's first of all evaluate the determinant. In the denominator we will have 6, then we'll have minus, and we have 1 multiplying 6 is 6, minus 6 multiplying 11. And that's it. Now, we can write this entry like this: 6 multiplying 11 minus 6. And this is basically, if I'm correct, 66 minus 6 divided by 6, and this becomes, let's write it here, 60 divided by 6. And furthermore, we can simplify this. We can, for example, divide this by 6, so we have 60 divided by 6 becomes 10. Consequently, over here we need to write 10, and over here we need to write 0, and over here we will have an additional 0. Next, we need to construct the entries in the fourth row. The principle is the same. The first entry is constructed like this. In the denominator we have 10, that is, we have this entry, and in the numerator we have a determinant of a matrix formed by using this column and this column. Let's enter this matrix. We have 6, 10, and over here we have 6, 0 with a minus sign. Then let's construct the entry over here. In the denominator we will have this entry, that is 10, and in the numerator we will have a determinant of a matrix whose first column is this column and the second column is this column. So we have 6, 10, 0, 0, and with a minus sign. Good. Let's now evaluate these entries. Obviously, this is equal to 0, and let's evaluate this entry. This entry is actually, in the denominator we have 10, and we have 6 multiplying 0. Let's put the minus sign over here. 6 multiplying 0 minus 6 multiplying 10. And this is obviously 6 multiplying 0 is 0, minus and minus becomes plus, so we have 6 multiplying 10 divided by 10, and this actually becomes equal to 6. And that's it. So let's enter the corresponding entries. Over here I will erase, and then I will enter the entries. This entry 6, this entry 0, and over here I will have 0. The Routh-Hurwitz theorem states that if all the coefficients in the first column of the Routh-Hurwitz table are positive, then the system is asymptotically stable. Obviously, here we have that 1 is positive, the first coefficient, 6 is positive, the second coefficient, 10 is positive, the third coefficient, and the fourth coefficient is 6 is positive. Consequently, system is asymptotically stable. I will write it down. stable. And that's it. And this is how we investigate the stability of the third order system. We construct the Routh-Hurwitz table and then we perform a simple test. We just check the positivity of the coefficients in the first column, and if the coefficients are positive, then the system is asymptotically stable. And that's it. By using the Routh-Hurwitz stability test, or better to say the Routh-Hurwitz stability theorem, it can be shown that in the general case, the conditions for the stability of a third order system, represented over here, where k, a3, a2, a1, and a0 are coefficients, is that, number one, all the coefficients of the polynomial in the denominator have to be positive. That is, a3, a2, a1, and a0 have to be positive. Then the product of the inner coefficients, that is the product of a2 multiplying a1, should be greater than a3 multiplying a0. If these two conditions are met, then our system, or better to say our transfer function, is asymptotically stable. Note over here that we can also change this first condition. We can also allow that the coefficients, all of them, have the same sign. For example, a3, a2, a1, and a0 can all be negative. Why is that? Well, we can just take minus sign, if they are negative, out of this polynomial, put it upstairs, that is, incorporated in k, and then again we will have all the positive coefficients over here, and consequently we can simply apply the Routh-Hurwitz test, which will guarantee the asymptotic stability of our transfer function. Okay, that's all for today.